M, this is for R greater than 2n, and V2 equal E V for n, W2 equal E minus W for n, R less than 2. You see, actually, I introduced this minus sign here. This is plus sign, right? So this is because it's on the inside, outside. dV bar dW bar equal 1 over 16 m squared E V W for m dV dW by R greater than 2m minus 1 over 16 m squared E V minus W for m dV dW. So we'll get this one. Sorry, this is theory now. Or you can actually get a dV dW in terms of as a theory. Or we get dV dW equal 16 m squared E W minus V over 4 m dV. R minus 16 m squared E. Right? No, we needed to actually check what's this guy. Remember we have the relations where you can see E W minus V for n equal R minus 2 n minus 1 E minus R over m. This is exact equal 1 over R minus m E minus R to R greater than 2n. So minus 1 R minus 2n E minus see? This is exactly what we expect, right? So now I guess I need 1 over R minus 2m factor. This is where I can exactly cancel my F term. And moreover, here is minus. I have minus here. Minus, minus, plus. Plus, plus, plus. So now you can see, okay. Then we find with this one, I can actually combine 18, 19, we get ds squared equal f is the f r minus 2 m r dv dw minus r squared d squared. So this is equal particular in like what I said. minus 2mr 16m squared r minus minus r 2m with minus r squared. See, now we get this part, right? Here, r minus 2m disappear. So from here, this actually you can read the component. So this actually, a letter you can check if you want. I really suggest you later just work off the details. And then say, okay, how the length correspond. You can have actually, you just figure out the length yourself. So this actually, in region 2, we have the following. T prime equal 2m minus r 1/2. This is y2m. Remember, I have a log absolute of r minus 2m. So when m r less than 2m, this actually counts. Then e for m cosine hyperbolic t over 4m and x prime equal 2m minus r 1/2 e r 4 and sin t 4. And this actually is called this reduce. This I call equation 4. This is equation 5. This is actually reduce. Now, let's see here. This region, I want to see where is the correspondence. This is the whole region, right? T go to minus infinity to plus infinity, r greater than 12. Correct? This is region 1. But you see, this area in this place, if a t go to minus infinity plus infinity, my t prime, same thing, to go to minus infinity plus infinity, right? But my x is positive because cosine is positive. So I have actually in region 1, I have a t prime, let's see, x prime you can see if I equal r equal m is actually equal. This is actually r equal. But this is not enough. Why? Because you see here, this factor, I forget one factor. This will be E, R over 4, and here, right? You see, for this factor, this is square, minus t squared. Then the cosine square minus 1 equal 1, right? So I have actually t, let me see, reading 1. I have x prime square minus t prime square equal r minus 2n, get the square, then e to r 4, right? But this actually always greater than 0. Correct? Because this always greater than 0, which means actually this is a TR, so I should have, this is the original one. Not only you see T prime from minus infinity to plus infinity, and also X prime from 0 to positive infinity, I always have this constraint. This is 45 degrees, right? So my reading 1, you see here, mapped to this part. Correct? In particular, this will be 0 when r equal to m. When r equal to m equals 0, this means this guy is equal to this guy, either plus or minus. So this actually my r equal to m, r equal to m. Correct? Here is also r equal to m, but I just simply extend, but remember we just put it here. Okay? So r equal to m, this actually vertical line becomes 45 degrees. Okay? Now I want to see what's happening in reading 2. In reading 2, here, my t prime, you see t actually always non-negative because it's a cosine hyperbolic. Could be 0 because of 1 r equal to m, right? So my t actually, t prime greater than 0. Okay. But my x prime, you see x prime, I have a sine hyperbolic. This part is always positive, right? And this is non-negative, can be 0. But if my t goes to minus infinity, this will go to minus infinity. If my t goes to plus infinity, this will go to plus infinity. Remember, this is really the one is t greater than r greater than 2n. This is by definition, this original. So this original actually, the t also greater than minus infinity, less than minus infinity, r greater than 0, less than 2n. Right? This is the region 2. So in region 2, I have actually x actually can go to from minus infinity to plus infinity. Right? This is actually my t prime always go up. Then x prime goes to the whole axis. Right? But I also have a constraint here. I'm going to raise here. T. R equals 0 singular R. You cannot actually cross R equals 0, right? What's the R 0? R equals 0, you see in region 1, you can put here I have actually r equals 0. I can simply from here, right? R equals 0, so p prime square minus x prime square equal r equals 0. R equals 0, 0 prime. Right? So one branch of this guy. This actually r equals 0 surface. So I'm actually restricted to this part. This is actually my region 2. So here you see, I have my region 1 here, my region 2 here. Right? Remember when we use P bar R planes, we find everything can go in, cannot come out. This is exact here. P is a singularity. Right? So this actually here, they can just, things can go in. So I have, let's say, this actually in the P prime, R prime, I have region 1 and region 2. Things only get in, cannot get out. This is my black hole. This is one asymptotic region. Right? Of 1 and 1 prime, I'm going to consider them actually together. So let's consider as the regions 1 and 1 prime. In that region actually we have x prime square minus t prime square equal r minus 2m E-R over 2 and T prime X prime equal hyperbolic tangential T over 4 and this X R. Okay, we do not need the number. Let's put this. Like what I said, because this is algorithm there, then let's consider one line, R equal R1, greater than, right? R equal R1 greater than 2m, then you can see I can use this one. This will give me x prime square minus t prime square equal R1 minus 2 and R1, 2, and This angle nothing more than alpha squared constant positive. The reason I use alpha squared because it's greater than it's positive. When this is a positive, we can see. Now I'm going to read. So this angle x prime minus x prime prime, this is equal constant. This is hyperbolic, right? So this angle is simply. This is a point at t prime equals 0, which means the angle x equals r. That's called r1, correct? So this angle, I have another one. This is minus. Because this is exact t prime x equals plus. That's symmetrical, right? What about if I have, let's say, r equal r2 greater than r1? Greater than r1, you can easily understand this equation. r2 minus r, right? This is a line. R equal constant. Then if you want to see my time t attribute, so this corresponds a line in this angle, right? R equal R1, R2 in the T R plane. Let's draw this thing. This R1. So this is two parallel lines that become this two. Correct? Now this angle is the time you will look in the right side. So this, oh sorry, I think this is not correct. This is a T, you written 2. This is going to be, this is the right. This is angle T, decrease, because this angle is a negative. Okay? So I have this angle 1, this is the R equal 1, in this range go this, and this range is go opposite. Okay. Now, what about R equal to M? R equal to M, this guy is equal to 0, right? So x prime squared minus t prime squared equals 0. And this is x prime equal plus minus t prime. This is exactly accurate. This is the line here. This angle where R equal to, and let's put it here. R equal to, and R equal to, and here R. This angle, the lines. Now, this is exactly 45. Now, this is actually the T R equal constant fluid. What about the T equal constant fluid? Now, let's say if a T equal T1, now if it's, let's say, first a negative, right? Negative, which is this like a negative, so we have like a T prime equal minus, let's say, beta 1 x prime, right? Beta 1 equal this like a T. So here is beta 1 equal minus tangential T1 by constant. So this actually one. This path actually equals 0 point here, but when T, this will go like this. Correct? And this actually, you see, when x prime equals 0, T prime equals 0, but when T is positive, this should be, let me see. Yeah, this is actually the case, right? This is actually T negative case. Let's say this not 1. What about 2? T equals 0. T equals 0, this equals 0. My T prime equals 0, right? So this is actually the line. T equals 0. This is a line, T negative. Correct? So, what about T equal T2? Positive like beta will be T prime equals beta 2 x prime. Now beta 2 is positive, right? So beta 2 is positive, this will go like this. Equal constant everything. So I have actually, you see now, from here T negative, they go to 0, they go to T positive. So this actually corresponds to T1, 0, and T2. But in this region, on. Correct? So I have, you see now, the T equal constant line, no, sorry, the T equal constant line here becomes the circle line in T prime H prime. But the R equal constant line becomes hyperbolic here. This. So if I consider this line, this side is T equal to this side T equal. So that's actually, now this is a mathematical. What's the meaning of physics? So I don't think we know this, right? Any question about this part? So this actually the 1-to-1 map between actually regions 1. Now we have here 1 and 1 prime. So we just actually give one like mu's. Here is T equal increase, here's T decrease. If T becomes constant, now actually T becomes this kind of line. How do you understand this? I don't think we know this. This is actually what we try to get the new physics from. Why do we hope? Right? Okay. So any question about this part? Then, if you do not have question, we will be region 2 and 2 prime. So if we consider 2 and 2 prime, prime, we have the following. 2 prime squared minus x prime squared equal to m minus r e r over 2 n x prime t prime equal. Here, so t over 4 n r prime, right? So now again, want to say, let's see, first r equal r sure less than 2n, right? R equal r sure, you can see here actually. T prime squared minus x prime squared equal to n minus r sure e r sure over 2. And this actually will still r plus sure squared, right? So there is a positive. The positives have a bottom. Parabolic, but now it's actually in the t direction. So there will be something, we don't have a current chart. We'll use this one. Let's see, this is what this one. This is a minus r, sure. This is r, sure, right? So this actually you can see here when x prime equals 0, t prime equals plus minus r. Plus r sure corresponds here, minus r sure corresponds. This actually minus r. Okay? So we get this one. Then you can say, okay, what's happening if I consider r equal r? This would be r sure, sorry. R4, first, let's see, less than r sure. Less than r sure, that's t prime squared minus x prime squared equal to mr4 e r4 and so I have this one, then you will this actually will be R4 here. This actually will be minus R4. This one. Okay? So what's happening? R equals 0. R equals 0 actually 2n. This is actually this 2n. R equals 0, this actually will be. The city. Okay? Now you remember, inside the black hole, R equal constant, R become time, right? So that's why you see now this actually like time. So this actually time have surface. R equal constant becomes time like have surface. So when R equals 0, this is exactly sitting at the top. That's why everything has to hit the time. Then R equals 0, right? This actually mathematically, this is mathematically makes sense. But what about here? Right? So this actually means everything comes out from that singular. That's why I have the bottom. Right? Any question about this problem? Once we get the same thing, we're going to repeat what's happening with the actual. Let's see, t equal constant. T equal constant, I think we can write here r prime equal t prime tangential t for n. Let's see, when t let's consider a t equals 0 case. This is whatever. T equals 0, x prime equals 0. X prime equals 0, which means this line. How do you understand that t equals 0 becomes straight line, vertical line, right? Because r prime equals 0. So t equals 0, we have like r prime. When t equals t3 less than 0, then we have actual x prime equals beta minus beta 3 t prime, right? So this will be the lines negative, so this will be this line, right? So this actually t equals t to the negative. What about t equals t4 positive? Positive now becomes actually x prime equals beta 4 t prime positive, right? I have actually. Or if I do here, this actually t negative. So now, if I come here, this is t positive t0. My t actually goes like this, right? Increasing for fixed R. So here is the cut. This is actually t equal. This is t0. This is t negative. So this is the time, the t direction in the slot chart called t. So this actually corresponds between t equal constant and r equal constant in this surface, right? So quite confusing. So now we try to actually understand what's happening here. So if I simply replace, get from my basic ideas, the structure between this plane and this plane. This is actually the one-to-one correspondence mathematically. How do we understand the physics? I think some part we understand, right? Like what I said, this is actually t equal, this is actually exactly r equal 0, this actually becomes time-like surface. This is our ceiling, our skies, everybody has instinct. So if we start from one hole from bottom, things come out, then just you can see this how they come out and focus to the formula. That's fine. But did we find this phenomenon? No, we didn't find this yet. We found actually black holes. So this is actually the series by the way, when we say we observe black holes, not really black holes. If you read the literature, even not a black hole, you can get some similar behavior. So supermassive black holes, we observe the Event Horizon Telescope observe black hole. You can see if you replace black hole by so-called Gravitational or any other object, still or above. Professor Sushant has been working on this in the work. Shadows, you can replace.
Tomorrow we will show shadow. Tomorrow shadow.
Yeah, this is actually the same. But if you think that this black hole is consistent with the answer, right? Until we find it inconsistent. Okay. So Now from this picture you can see region 1, this one. Region 1 actually, I'm actually talking about this is called region 1 prime, right? Region 1 prime has the following properties. X prime less than 0 and t prime greater than minus infinity. And then x prime square minus t prime square goes to 0. This is actually exactly the corresponding here. Remember we have a square structure. So if I actually, okay, so this actually is the case we have, I think in this case. So now we have also region 2 prime. Region 2 prime is this region here. Region 2 prime, I'm going to write here and then explain. So this I got t prime greater than infinity, less than equal to 0, and x prime greater than minus infinity plus infinity. We always have t prime squared plus x prime squared equals 0. So again, there is singularity here, r equals 0. This is where I actually make it the bottom boundary. You cannot cross here. So this line will asymptotically go to the dollar r equals 0. Correct? So this actually you can see now, if I look at the following. This actually, the lines, I have region 1, 2, the line come out for a narrow asymptotic flat region. This is the one we talk about. Remember we use T stars and T star planes and R planes. That's exactly 2 prime, 1 prime. Okay? I have a wide hole to the asymptotic region. Right? And also can be here. Right? This is also wide hole connected with this asymptotic region. You see? There's 2 possibilities. The wide hole connected with here with this region. This actually 2 prime with a 1. So there actually we are not so specific. Here this can be 2 prime to 1 or 2 prime to 1 prime. Right? The same thing, the black hole region here, we can see it's a 1 prime to 2, 2. Right? This is confusing enough, right? So this actually tells us, okay, the mapping, now I unify actually T bar R bar plane and T star R plane, but I get this kind of connections. I have region 2 prime wide hole, region 2 black hole. There are 2 asymptotic regions can connect either wide hole or black hole. So here you see this is wide hole connected with 1 prime, wide hole with 1 region. This is actually 1 connected with 2. This is actually 1 prime connected with 2. Either is okay. We have asymptotic 2 asymptotic regions. Right? So do we find this universe? Oh, this construct in our universe? So far not. So we do not know if it exists or not. Normally we think this is the analytical mathematical interpretation. So physically we think only half of them make sense. Like what I said, who knows? some people propose I have a white hole emitting something because the attraction they focus they form a black hole. I have something like this. The white hole emit a particle converges and then finally collapse and form a black hole. Okay. In 1980s or early of the 90s, some people construct this kind of solutions. So numerically. So half numerical, half analytical. I have white hole emitter particles not stable, then comes because the attractive forces so they are focusing each other, then form a black hole. Finally collapse. Yeah? So this is actually the picture. Now we want to see, okay, I want to find out, remember, from very beginning we just know the relation between 1 and 2 with a t prime, x prime. I want to see what's the relation between 2 prime and 1 prime. Because only I find exactly the corner transformation, I know what's the map between 1 to 1, right? So then I can try to understand the physics. What's the meaning, right? So this is actually the next step. I want to please pay a little bit of attention. So this actually sometimes very easy to get confused here. So this our goal is to find a corner transformation between actually this actually in this region 2 prime between TR and T prime X prime, in region 1 prime between TR, T prime X prime. Or you can use W tail and with tail. Now to understand this, we first notice the following. In region 1, because region 1 is actually just simply a reflection of the region 2, region 1 prime. So if we understand region 1, then we know what's the map between TR and T prime X prime. Right? So in region 1, you see actually region 1 we have X prime square minus T prime square equal R minus 2n E R over 2 and T prime X prime equal yes of T over 4n. This for R equivalent, right? Region 2 we have T prime square minus X prime square equal to R minus R E R minus 2n X prime T prime equal use of T over 4n. Okay? So this is actually the case. Now from here, I can get my T, the substitute, right? I'll first consider region 1. So let's still keep this for a while. Later I will erase this part. So I have X prime square minus T prime square equal X prime square minus T actually equal X prime square tangential hyperbolic T 4n, right? This is what I have here. Then I can write this actually equal X prime squares cosine X squares T over 4n So this angle equal r minus 2n e r over 2n, right? So what I did, substitute here, then I can get r prime squared. You see here, r prime squared. Then it's still equal to r. Now I just look here, my x prime squared equal r minus 2 and e r 2 and multiply cosine hyperbolic squares t over 4 and right. Now I can get my x prime. So then I have actually so I still want to use this part, huh? So then from here I can x prime square, x prime equal plus minus r minus 2 and 1/2 e r 4 and cosine x t 4 and hyperbolic, right? So from the reading 1, I get this one. I get 2 solutions. But we know reading 1 actually x prime is always positive, right? Where is x minus? X minus is exactly 1 prime, really, right? See here? Because this relation is actually holding x prime too. So now I have 2 solutions here. One actually is region 1, another is region prime. Okay? So this is actually how I get actually the solution. If I have actually x prime negative in region 1 prime, I have t prime equal x prime multiplied, right? So then you can see now I'm going to write this one. My x prime equal negative r minus 2n 1/2 e r over 4n correct? Then this is also true in region 1, so I just simply my t prime equal x prime multiply this guy. So multiply this actually, I write this equals sine over cosine actually cancel, right? So I simply actually write this equal minus so prime So this is actually the coordinate transformations between RT and x prime, t prime, you read 1 prime. I think in my notes, here the cutoff is this purpose. This is actually, I think in pages 57, you can see the last line, actually half of the cut is the right line. Okay? So this angle gives us actually how we can get from reading 1 to 1 prime. Actually, I just simply use this. There are 2 rules. One is the positive, and another is reading 1. Because the reflection symmetries, this is just simply take the negative rule. Negative. The negative, once I get an x prime in terms of TR, I get actually also T prime because T prime and X prime, when they actually T prime or X prime is equal tangential resistance. Okay? Any question on this part? You see here what I get actually from here, this reading, I use the phone, I use actually the symmetry. So this is 2A rated symmetry. The only difference actually, one in this one is a half X prime negative, in this prime X prime positive. Using this fact I get here, then I get 1 prime. Okay. Any questions about this part? So now we're going to use this one, the same trick, to get actually 2 prime. To get 2 prime, again, you can see now I'm going to get this actually X prime equal T prime put in, right? So I want to see what's happening. You raise it 2, then you can say, okay, T prime squared minus X prime equal T prime squared tangential squares T over 4, and this actually will give me actually T prime squares cosine parabolic T 4, and this actually equal this part, right? Equal 2 m minus r e r over 2. Okay? Now I can get my T prime equal this. So in this case, I get actually my T prime. I'm going to write here, T prime equal from here plus minus 2m minus r 1/2 e r over 4m, right? Cosine parabolic t over 4m, right? So this, but we know you really 2 T prime is negative, right? Only 2 actually T prime positive. So what I do is just simply choose minus sign, right? Once I get a T, I have this resistance, I can get my X. So my X prime equal, this actually again is minus 2 m minus r 1/2 r 4 m. Okay, so I'm going to erase here. So I get all the actual one-to-one correspondence between this actually T R prime to the T prime X prime prime. So otherwise I cannot get a one-to-one because actually it's not a one-to-one. It's a 1-to-2, right? So that's why here 2 radians I get a 4. But I needed to figure out how to get a relation in the extended radius, 1 prime, 2 prime, right? So it's a very complex case. My experience is the following. Try to figure out yourself, then draw the lines. Then you will understand much better the corresponding line here. Okay? So this actually is the whole process. It's very standard. You can use this to generate other cases. Any questions about this part? The whole picture you can see. So what I suggest you please go back, really use this kind of relation. Try first to understand how to derive this relations. If you work on the new solution, can you do the same thing? This is actually the basic This is what they really want to learn, right? Want to apply. Second, draw some lines, try to understand the map between this plane and this plane to see if you can figure out your field. And later try to understand what's this one, what's this plane, right? So this is actually the same thing. Today we finished earlier, right? We're going to start here. You want to take some photos?
Yeah,
right?
here. First photo here, and then we go down.
Oh, okay, good.
Then here.
This actually gives the map between T R coordinates and T prime X prime coordinates in each of the four regions. So next we just want to say, okay, let's see if in this region R equal constant. This is R equal constant, right? What's the corresponding in this two regions? And in this region R equal constant, what's the correspondence? Then we understand the structure, right? So here, let's see, T equal constant here. This is T equal constant negative. What's the corresponding H of the region? Then we want to say, oh, now you see, in this region, when I see the T equal constant here surface, what's the corresponding in 1 prime and 1, right? So this actually, next step is, this actually is the most difficult part. If you can follow me, that's like perfect. Otherwise, go back to read my notes. Then get the correspondence. Okay? This is also the most difficult part because when we do together, it's all so easy. I can easily follow. But when I give you a new problem, let's see, I have a solution. You make the extension. Find the one-to-one maps. Then you will find, oh, there's some details I need to pick up. So when you have this problem, no problem. Do not actually never still come back to my notes. You work at it. Okay? So that's enough. And let's say number is fine. Okay. Any questions about this part? You understand what's happening is that we have these two regions here. We have 1 prime, 2 prime. I will erase here, huh? Because I needed a figures. So, yeah. Any question on this part? Okay.
We are still interpreting them. So that is what creating the confusion.
Yeah, we can actually, you see, because on the very beginning, our metric is singular, so physically we either work in region 2, which is inside the black hole, or either work in region 1. But we cannot actually make them together, right? So we just like adding the figures and they realize, okay, using my counterterminus, I can connect 1 and 2. But they didn't realize this bring actually more confusing, right? You want T bar, R plane, you have black hole. In T star, R plane, you have white hole. So how do I understand? This part of us long time.
Since the thing is, once we keep on doing these transformations, how do we assign the meaning to each new coordinates that we find? Means up to Eddington Finkelstein, it was tractable. But after that, whatever you did, it is simply mathematics.
Yeah, you're right. That's what I really emphasize. This is like pure mathematics. Mathematics in the sense of regular mathematics. So that's why I regular mathematics and pure And also there is no any approximation, everything analytical. Now, what's the physics? Because we are the physics, right?
Yeah.
We need to figure out the physics.
Okay, that's just one question. When we are interpreting these diagrams,
Uh-huh.
and when we are trying to say the particle is going this direction and this direction, or it is going in this direction and time, in that moment, the time that we are referring to, is it the time of the first coordinate that we started with, or it is in between some transformed coordinate that we are talking about? That is what I'm asking.
Yeah, that's very good question. The answer is no or yes, because the time, for example, you can use your time.
Okay,
I can use my time,
okay,
right?
yeah,
So remember, once we are inside the black hole, the time coordinate t becomes space line.
yeah,
R becomes time. So they just switch the directions.
yeah,
So now let's say, okay, if I'm, let's say, if both of us, let's say you really want, you use your t, I use my t prime. That's fine because we have one-to-one correspondence, right? So you know, okay, since we know one-to-one correspondence, even for example, your time is increasing, my time decreasing, that's fine because we know how to correspond, right? The problem is, what's happening if I'm actually really one connect with two time? Can you compare? This is a physics. We're still struggling with it. If we understand this question, actually we understand how structure, what's it mean? Right? For example, here I have time. Now you see I have R. R, like what I said, this becomes timeline.
This R, that R equals to 0, thus that R is the first singularity that we are referring to, right? But we are working with the diagram is drawn with respect to coordinates after a lot of transformation.
Yeah.
So that is what creates confusion. That is what I'm saying.
Yeah, this could not confuse to you,
It
like
is
to
like,
everybody.
it
Yeah.
would be a lot better if like the singularity is also
Ah.
transformed in terms of the new coordinates and it is drawn according to that. But it is not generally found either everywhere in this way. The singularity is also transformed in terms of the new coordinates and then the whole thing is drawn.
Yeah, the whole thing is, you see, the problem is because inside the black hole, the space-time becomes dynamic.
Yes.
Outside is actually static. So that's actually the black hole nature, right? So now you see, so as chart coordinates profit, okay, we can easily understand. But the problem, so as chart coordinates has singularity.
Yes.
How do you connect outside the black hole and inside the black hole? So that's why we are forced to find new coordinates, make the coordinates disappear. Because physically, if you have scalar singularity, you cannot connect the physics into regions. Because coordinate singularity, the coordinate becomes singular. So there are no direct connection. So that's why I want to, the first thing, mathematically, is okay, I'm going to find a coordinate which covers the two space.
Yes.
Right? Then in that coordinate, since I do not have singularity, which allow me to get in, get out.
Okay, one more question. Suppose we started with the coordinates which are a lot more physically understandable. And in those coordinates we do find some issues with connecting the two different regions.
Yeah.
That's why you are doing some coordinate transformation which is able to eradicate that problem.
Uh-huh.
So means the thing that the physically viable coordinates is not able to connect it. Which physically understandable coordinates are not able to connect two different regions, but
Yeah.
a mathematically transformable coordinate is able to connect it. So what should we prefer? Means it's just a question of opinion. I'm not asking.
Yeah, this is a kind of opinion. Oh, this one is okay. I understand the physics.
Even necessary means because if we mathematically they are connected, we are
Uh-huh.
showing it using coordinate transformations.
Yeah.
But when we are using physically understandable coordinates in which we can track what is time, what is distance, what is angle,
Yeah.
we are seeing that it is disconnected.
Yeah.
So does that anyway imply about like it is just mathematically it is possible, but physically it is not?
Yeah, this is exactly the main, the critical point.
Yeah.
First, mathematically we need.
Hmm.
What's the physical implication? Does mathematically correct really always bring new physics?
Yeah.
Right? This is actually your
Something
question.
like that, yeah.
Right?
Yeah.
So now, I think the answer is so far, after 100 years, we're struggling. The answer still we don't know. So that's why, if you look at the black hole history, people, wherever you heard this working on thermodynamic black hole, you have actually firewall, all those things. Why we propose this kind of ideas? It's exactly because we do not understand where role, what's happening near this horizon. So in certain sense, okay, this is mathematically correct. Then this bring new physics.
Yeah.
If you look at the history of the science, they will sometimes do,
Yeah.
right? For example, unless, let's say, forget this diagram. We have a color singularity, then we understand there's a black hole. We do observe black hole, right? Einstein still predict the existence of black hole. But we observe. That's new physics, right?
Yes.
Because we are forcing the mathematical pathology of the colors that bring new physics.
Yeah.
Now the next question is, does the whole picture of any part make physics?
Yeah.
Right? So the answer I think is no. But the answer is that we do not know. That's why we are still struggling. Okay? So this is actually, yeah. Okay. Very good. Any other questions? Okay. So now we want to, like what I said, to say exactly what's happening. Now we go to details. We understand the quantum transmission between each regions. Now we want to see how we can explain it. Here is the R equal constant, which is R equal constant at the surface. What's the corresponding here, and here, and here, right? And what's the time t equal constant at the surface? Then we get a better understanding, right? So this actually is, again, this is a mathematical understanding. Sorry about that. So, but this is like an introduction. So our idea, like what I said, we want to see what's the connections. So you will see, we will have some, this actually our R equals 0, have certainly R equals 0. Then this actually R equals constant. We'll work out one by one. So one of the important tests is you will find, okay, this is the case. So how do I really express my coordinates t prime, weight x prime, or weight period and double period in these four regions? Of course, now we're saying R greater than 1, we already have. This is actually we call the region 1 region, actually. This is actually region 2. We know the corresponding. The program will figure out what's the R prime and 1 prime. Once we know this is the map, then we know how it corresponds. This is actually the test. So mathematics are a little bit complicated. So that's why I think I want to slow it down, explain something in details. So this actually we use this is called double null coordinates. But this actually called, this is the UV. Now we want to introduce actually T prime. T prime, we want to use this 1/2 V0 plus W0 minus X prime equal 1/2 V0 minus. I think in my notes you will see I use prime, so I still keep the use of V0. So this actually, they are equal, okay? So I will use this one. Then really you can see this is 45 degree, this will be exactly, this is 45 degree, right? So because this is resistance, if this actually 45.